There we go. Not distill. So this is beta decay. Notice that the way to remember this, and they do want you to remember this. I don't know why. This is a fairly obscure bit of particle physics. But the anti-electron neutrino is emitted with the regular matter electron. And that's because there's a number that's conserved here called lepton number. This one has a negative number, that one a positive. Therefore, the total number of leptons created is 0. Yeah? Okay? The electron neutrino here has a positive number. It is a regular lepton. But the positron is an antimatter lepton, so it has a negative lepton number. Therefore, you have a negative number here combining with a positive. We haven't created any more new leptons. Crazy. And what is a lepton? They are things like electrons, taus, and muons. They're a type of particles, and this is particle physics, which they cut. So we don't need to learn that, but this little bit, this little vestige they want you to know. So just remember that matter and antimatter, if you create a matter one, you've got to create an antimatter one. If you create an antimatter one, you have to create a matter one. That's the conservation that's going on there. Right? Spontaneously splitting apart. The question is, when you say decay, what do you mean? It means spontaneously splitting apart. Like this, here. There are atoms in there right now that are spontaneously splitting apart. Every beep is one of those detection of the radiation from one of those.
I have an interesting story.
Yeah.
So I had a bone scan done on Friday.
Yeah.
And the way they do this, they inject me with a radioactive ice.
Yes, they do.
Yeah, so I had technetium through me, and
Yeah.
I'm undergoing gamma decay for like the majority of that day.
Yeah. Yeah, we should have gotten the Geiger counter.
I wanted to come in here and have you put this
I know.
on me, but I forgot.
I know, well, there we go. And even then, I imagine that it would be hard. We'd have to take like data for like 10 minutes to determine the difference between you and just the room, right? So it's not a huge amount of energy.
Actually pretty interesting because the machine they had scanning for it, they showed me the screen, and like before I could see the like photons popping up in the screen very like sporadically though, very low concentration. But then they put my legs underneath, and like I could immediately see the outline of my muscles and like darker outline of my bones.
Ooh, that's kind of cool. So it might be a little hotter than we think. Short-lived though, yes?
Yes.
Yeah.
6-hour half-life.
Right.
And my
Okay.
kidneys excreted most of it, so.
That's good. This is a good thing. I know. It doesn't. Okay, so can we focus? We've got to go faster than this. Okay. So this is Wolfgang Pauli and Enrico Fermi, and basically when they looked at beta decays rarely, the beta particle rarely had the energy that it needed to have to account for the energy of decay. Okay. What this means is that if you look at the mass of all this stuff on the right side, and then all this stuff, by the way, did not include the neutrinos. If you look at this mass and this mass, this mass and this mass, the beta particle never had that much mass. Sometimes it had close to that much mass, but there we go. In fact, energy, it never had that much energy, right? In fact, the amount of energy that it could have was the upper limit to what it would have, and generally it had less than that, right? And so either energy is not conserved, or there's a very hard to detect particle, the neutrino, right, that's carrying away some of the energy. And Pauli supposed that that particle existed. The alternative was to discard entirely conservation of energy, yeah, for this thing, right? And so basically, Fermi, who's Italian, names it neutrino, right, which is Italian, not italics, for little neutral one, yes? Okay. Neutrino just means little neutral thing.
So is it a neutron?
No, neutrino is a particle, and they're all associated. They are leptons, right? We believe they have some rest mass, but they're very, very hard to detect. There are billions of these passing through your body this very second, some of them from enormous stellar explosions from the other side of the galaxy. So these particles are the holy grail for physicists that are looking at the universe. Okay, they are the cosmologist's holy grail, and here's why. Light has a hard time getting from one side of the Milky Way to the other, but neutrinos can pass right through everything. So if something exploded on the other side of the Milky Way, we could see the neutrinos from that explosion over here, and they would be largely unchanged. This is a beautiful thing. In fact, we could see neutrinos all the way across the galaxy. Yeah, all the way across the universe, I mean, right? Okay, so if we can make a telescope that uses neutrinos somehow, right, and there's really some good ideas of how to do this, then we can look at things from a long time ago and very, very far away and we can answer all sorts of questions. Yes?
But wouldn't it be like, because they're not affected by anything, that you're just looking at them, just sitting there like coming at you?
Yeah, but they're going to come at you at particular energies and from particular directions.
Oh, so you're
And
saying that like from the decays they're going under the being
they're not all coming from decays. There's things like supernovas. There's something called neutrino refrigeration, where a lot of the energy is given off as neutrinos, right? And so specifically, we're very interested in that.
So by like the concentration and the energy they have and stuff, we can interpret.
Yeah, there's all kinds of stuff. There's all sorts of information on these things.
What speed do they travel at?
Close to the speed of light. Yeah. We think they have rest mass, so they can't go the speed of light. You know? Okay. So in 1956, we did not detect neutrinos, but we did a mathematical confirmation of their existence. They were detected first, I believe, by the Super K, these are hallways that people can walk through. So this is a ginormous tank of water. It is hidden deep within the center of a mountain, kind of like, a James Bond movie, only far fewer weapons, Okay. And the notion is that each one of these little dots that you see on the edge there is a photomultiplier tube. These are things that are just crazy sensitive to light. They're absolutely fantastically crazy sensitive. They're thousands of dollars each. A good photomultiplier tube is probably in the order of $1,000, right? And these things are actual vacuum tubes. We have nothing better than them, I believe. And the walls of this tank of water are lined with those tubes. The Super K, by the way, died because some scuba divers were in there cleaning it, and one of them accidentally broke one of those vacuum tubes. Well, when you break a vacuum tube, it sends out a little shock wave, and the shock wave breaks more. And you can figure out what happens there, right? Yeah, this is sad, right? Okay. They broke a lot of isn't that sad? Here's how it works, though. If an electron neutrino, where it goes through water is a good way to have a lot of electrons sitting around, right? And so if it encounters an electron, if it happens to interact with an electron, which is, the probability is vanishingly small, but we have a lot of water, and we're going to detect it if it happens, right? Okay. If it hits an electron, it accelerates the electron to faster than the speed of light in water. Now, you can't go faster than the speed of light, but you can go faster than the speed of light in water, can't you? And that's because the speed of light in water is like something like 2.24 something times 10 to the 8th meters per second. It slows down in water, right? Okay, light slows down in water. So you can go faster than the speed of light in water, yet slower than the speed of light, correct? Okay, so an electron traveling faster than the speed of light in water actually makes something like a sonic boom. When you go faster than the speed of sound, you make a sonic boom. When you go faster than the speed of light in water, you make something called Cherenkov radiation, right? Which is, by the way, the glow when you see like the stuff sitting in the holding tanks of these power plants, right? And they take a time-lapse picture of this. Yeah, I don't think you can see it with your naked eye, right? That glow that you see, that's Cherenkov radiation, this eerie sort of glow, right? In water, yeah. Okay, so the sensors on the wall can pick up the distribution of the photons, and I'm getting over my head. I don't know exactly how they do it, but they can analyze that and determine that this was an actual Cherenkov radiation and not something else, right, going on. Okay, so gamma decay is just simply a transition. The numbers don't change. You're not losing any mass. You're not losing any charge. It's just a photon. Okay? Now, what I can do here is I can actually act out a gamma decay for you. Okay? So what you're going to see at first is the nucleus in an excited state. Okay? And then I'm going to emit a radiation, and I'm going to be in a more or less excited state. I'll be in my ground state. Okay? Are you ready for this?
Yeah.
Okay, here it goes. Ah! You see how calm I am? Do you want to see that again? Yeah. So again, you'll see the nucleus in an excited state, the daughter nucleus in an excited state. So these things happen, by the way, after decays. So like, this is not just plutonium. This is plutonium that probably has just undergone a beta decay. It is the daughter nucleus of a beta or alpha or something like that, right? Okay. and it's left it in an excited state. It's like